Bienvenue à cette troisième séance de notre séminaire autour des structures de contrôle. Donc l'exposé d'aujourd'hui sera en anglais, so I'm going to switch to English. So we have the pleasure to welcome Andrew Kennedy, who works at Meta in London. So Andrew is, he's an expert in functional programming, programming languages and their implementations, and especially functional languages. So when he was at Microsoft Research, he was, I guess, the main designer of generics in the .NET virtual machine. So if you have generics in C# today, you should thank Andrew for that. But he's also been working kind of on, in other projects, especially on his standard ML compiler, which uses continuations as inside as an intermediate representation. So he's going to talk about that. And I hear he's found other uses for continuations in programming language implementation recently. So thank you, Andrew.
Thank you, Xavier, for inviting me and for that very nice introduction. And for a lovely talk. I tried to understand the French, but at least the OCaml was in English, so not so hard. Okay, yes, so I'm going to talk about compiling, but also typing with continuations. So as you know, continuations are one of the best and oldest ideas in computer science, with many, many applications. Here are a few. So we've already seen, I think, with Xavier's talks, some of this. I mean, I guess the semantics is one place, but also I'm going to talk a little bit about compiling. But it's a generally useful concept for programming as well as for programming language theory. So I'm going to give a couple of examples before I launch into my main topics. So here's one, sort of thinking in the kind of continuations mode. So this is something I did a few years ago with Nick Benton at Microsoft Research. So we were looking at exceptions. And if you look at OCaml's try with construct, it's the usual way one does exceptions in a functional language. I mean, standard ML did the same. But sometimes it's kind of clumsy to use. And it's hard to put your finger on why or what would work better. And if you look in this paper, we give examples of from programming, but also from semantics, for why this construct is not quite maybe what you always want. And the solution was really to sort of think in terms of continuations. And Xavier has already kind of introduced this in a way, because the effect handler construct is very similar to what I'm showing here. So a better behaved construct for exceptions has kind of a failure and a success continuation, which is what you would get from double-barreled CPS, or as I learned today, the French, what was it, à deux canons? Learned some new French. So perhaps one wants a generalized let construct instead of the existing try with, where you have an exception handler. So you're binding a variable to some expression, but you have an exception handler for the failure case, as well as a continuation for the success case. In fact, in OCaml, 10 years ago, they introduced this generalized match construct, which serves the same purpose. So we have matching on successes, and then an exception to handle failures. So you've got multiple continuations. That's one example of sort of thinking continuations when working in programming language design. Another example, which something I did a few years ago also at Microsoft on machine code, we wanted to come up with some sort of program logic for machine code. Now, the usual way you do program logic dates back to Hall logic from the 70s, where you have these triples. So you have some code, which is C, and then a precondition and a postcondition. So this kind of means if the program state satisfies some predicate P when you enter the code, then it will satisfy Q on exit from the code. But another way to think about this is breaking it down into something a little more primitive, which is what we did for machine code, where you have a primitive notion of it's safe to run from a certain point in your program under some precondition P. And let's write that as, safe LP, safe to run from L under P. But then we can recover the kind of triples just by doing a kind of continuation passing thing, which is we say it's safe to run from the exit of the code with some state invariant Q if it's safe to run from the entry. And we use this to give a program logic for machine code, sort of thinking about this continuation-like notion. So I'm going to talk about two things today, the main topics of the talk. Well, the first is compiling with continuations, which we've seen a little bit already, I think, with all of the CPS translations that Xavier has presented, but also typing with continuations, which actually dates from my time at Meta. So I'm going to show you something that we've actually used it for at Meta. But first, I'm going to give a kind of overview of compiler intermediate representations. These are what happens inside a compiler, the kind of the languages that we use to represent translations from source code all the way down to whatever it is you're targeting. And for functional languages, one could just work with some kind of desugared abstract syntax, or maybe something more like the lambda calculus, but without any particular restrictions on how the lambda calculus is used. Or more popular in recent years is some kind of reduced form of lambda calculus where you have kind of names for everything. This is called ANF. A similar language based on monadic, on monads, you might call a monadic intermediate language. And then finally, continuation passing style, which used to be popular for compiling functional languages, less so now. For imperative languages, again, you might do some kind of desugared abstract syntax, but it's more likely that you're going to use some kind of flow graph with local variables. Or perhaps what's most popular these days for compiling imperative languages is called SSA. I think Delphine Demange gave a talk about that last week. Static single assignment, and variants on it, such as gated SSA. But again, you can use CPS to some sort of CPS language or a CPS transformation to compile imperative languages. And you can sort of see the first bullet in these examples is much closer to the source code, and the one at the bottom, say CPS, is much further away. It looks quite different. But let's start by thinking about functional languages. So ANF, so this is administrative normal form, a very clumsy term really, but and there's a history for why it's called that. But essentially, you're naming every intermediate computation. So here, in just a camel syntax, if you take, say, the recursive map function and then translate it into something like ANF, you're basically giving a name to, applying f to x, and you're giving a name to the result of calling the map function recursively. So every intermediate computation gets a name. And monadic intermediate language is similar, except that lets can be nested, so you can have let y equals let something. And monads provide a kind of place to hang effect information, so they're popular when you've got some kind of effect analysis over the program. But again, the order of evaluation is made explicit, that's the point. You're naming every intermediate computation so you can see what order things are evaluated. Now, continuation passing style also gives you this, but in a slightly more complicated way. You are basically, every function takes an additional parameter, which is the continuation, where the result gets passed. And so you can see in a camel syntax again, if you CPS convert the map function, then you're making the order of evaluation explicit by passing a continuation for every in computation. Now, the transformation is easy to write down, but it kind of explodes the code with a lot of new functions. So there's a lot of lambdas in there that weren't there before. And it kind of messes with your head to think about, but compilers don't care. I mean, It's just difficult to read as a programmer. So why compile using CPS rather than one of these other intermediate forms, which seem a bit simpler? I mean, A and F is pretty readable and comprehensible. So I think historically, it's when languages that support first-class control operators like call CC, so examples of that would be scheme and typed racket and standard ML of New Jersey, there's a very straightforward CPS implementation or translation of these first-class control into, it's essentially, when I say a CPS language, that's slightly misleading. It's kind of the lambda calculus, but you're doing this transformation from the lambda calculus into the lambda calculus, but with these additional continuation lambdas. And the second reason, and this was advocated in Andrew Appel's book, Compiling with Continuations, a few years back, every function call becomes a tail call. So we don't actually need anything like a call stack because every function kind of just jumps to the next one. And so all functions become closures, which we just allocate on the ordinary heap. So instead of stack frames, we have these environments on the heap. But you might be concerned that that comes with a performance cost because the stack generally is implemented very efficiently on a microprocessor. And having to allocate on the heap may not be so efficient. And there was a long debate a few years ago about whether this was really the case. But I'm actually going to be using continuations for a slightly different purpose, which is that CPS translation makes for a very uniform, simple intermediate language in which we give names to every intermediate value, but also every control point in the program. So some static analyses, this was my experience at least with the work that Xavier mentioned that I did at Microsoft, they become much more straightforward. And some optimizations, and you'll see one later, fall out really easily from once you've done this translation. There are a few sort of problems as well with the other approaches, so A and F, which the CPS language I described doesn't suffer from. So, and this is kind of well known in the literature, but you kind of have to get round it if you're using NF for your intermediate language. And one is that it's not closed under inlining. So here's an example. You've got a lambda that's immediately applied to some value. And obviously, you want in your compiler to inline the function. So you beta reduce or inline, and you end up with something which, strictly speaking, is not now in ANF, in administrative normal form, because that doesn't allow nested lets. So you then have to do this step of kind of renormalizing, which you move the lets around to bring it back into ANF, strict ANF form. That seems straightforward, but it gets worse if you have conditionals on the right. So here, suppose you had a conditional in the body of the lambda, and now we've got a conditional bound to a let, which again is not in ANF. And how do we renormalize that? Well, there's two ways we can renormalize it. One is by actually duplicating I'm going to say the word continuation, because that's kind of what it is, M here. So we end up with two copies of M in the term. That's not good. We end up with code bloat. Or we introduce a lambda to represent what's sometimes called a join point. So here we're sort of abstracting out this M and then calling it in both branches of the conditional. Now I've called that K, suggesting a continuation, because that's kind of what it is, this join point. So I'm going to come back to the CPS language now. And the idea here is that I'm not going to use continuations to represent first-class control, like call CC or delimited continuations or all of these fancy features. I'm just going to use them to compile an ordinary language without these features. But I'm going to name all continuations, and they're going to be distinguished from ordinary functions. So they're not general lambdas. So in this kind of suggestive syntax of OCaml, I've put let cont here. So the CPS translation introduces these continuations that have been given names. So it ends up looking rather contorted and kind of weirdly nested, but I mean, for a compiler, that's fine. So we've got this local continuation definition and a continuation application, which are kind of syntactically different from ordinary function application and ordinary lambda definition. And there is ordinary function application, which takes an additional argument, which is the continuation. Okay, so this was work I did a few years ago. So I had this paper, Compiling with Continuations Continued. And I'm kind of pleased to see that it's kind of made its way into practice now. So there's this work on the OCaml compiler, that some of which is carried out by Jane Street and OCaml Pro. And they've got an intermediate language called F lambda 2 that essentially looks like the language that I proposed. And there was a presentation at the OCaml developers and implementers work. I can't remember what the workshop's called now, but the OCaml workshop last year. Okay, so here's a very small version of that intermediate language. So we have values, which are pairs, say, and data constructors, and lambdas. And you can see that the lambdas have taken additional parameter, which is the return continuation. So all values are named. And this is the local continuation definition that you saw in the OCaml code on the previous slide. And there's an explicit return continuation for every function. And then, like I said, separate constructs for continuation application and function application with a return continuation. Now, there's a kind of design choice here. So in the paper, I had even the branches on like a match constructor or conditional are named. That's kind of a design choice. It's not quite so important for what comes. But, so just to summarize again, the features are all intermediate values are named and all control points are named. And a couple of consequences from this. One is that we only ever substitute variables for variables. We don't ever substitute actual values in. And the thing that I introduced to deal with, to avoid duplicating when we were trying to float a conditional through a let, a join point, they're present from the start. So when you do a CPS translation into this language, you've got join points there already. But continuations are second class in the sense that they can be passed to functions, but they can't be returned, they can't be stored in data structures, and they can't be accessed from functions out of function scopes. But a consequence of that is that they just represent blocks of code. So a definition is just a block, and continuation application is just a jump. There's a kind of open question, which I've never really resolved. I don't know whether other people have since I did the work, is how you kind of nest the continuation definitions. So there is actually a similar language which is used in the compiler called Milton, where they have things that look like continuations, but they're closed, completely closed. They just take a bunch of parameters and there's no free variables, and they're defined at the top. But in the language I described, there's a kind of choice. You could push them all the way down, minimize the number of parameters they take. And I'm never sure really what works best. That's something I've not really resolved. But it is closed under inlining. This isn't the language really that I described. This has got not named continuations, but you can see that basically I'm just doing beta reduction for the argument and the continuation. This represents the code we saw earlier. But here's the example of a conditional that we had earlier, translated into my language by CPS. So the point is that when we reduce, say, that, I mean, effectively we've got this lambda f, which is bound to f, and then we're applying it to J and C here. And we can inline those, inline the whole definition into here. But we've already got this join point from the original CPS translation, so there's no need to introduce something to avoid duplicating terms. It's just there. So the whole thing, the form is kind of closed under inlining. So I'm going to talk a little bit about how you would actually implement this in a real compiler, because I think that's kind of interesting as well. So you could implement it just in the usual kind of functional style, where you have like an algebraic data type to represent the expressions, and then you do transformations by essentially making a new copy, but with deltas. Now, that's generally expensive because you're doing a lot of copying. And an alternative is actually to represent the CPS language as a graph and do kind of update in place. And this can be extremely efficient. So this is an adaptation of some ideas from a few years ago by Andrew Appel and Trevor Jim. And you can make substitution constant time. You're just substituting variables for variables. And if you want to do a whole bunch of rewrites that do simple things on terms to compile them, then that can take just time linear in the size of the term, which is much harder if you're trying to copy things. It's not going to happen. And there's 3 ingredients. It does get complicated and it's quite hard to implement and get the invariants right, but it does produce very efficient compilation. So you have a kind of a tree for the basic structure of the terms, which is doubly linked, so you can go back up as well as down. And then for the variables, you link the bound variable for the lambda with all of its free variables in a circular list. And then finally, in order to get from the free variables to the bound variable without having to navigate this circular list, you can use a union find data structure. So it looks something like this. So this is an example where you've got links from, I think you can see the circular list. Yep, so if you look at P, there's a link from the bound variable P here down to its uses, and then a circular list joining all the uses. And then layered on top of that is actually a union find data structure, which means you can get from the occurrences to the bound variable very efficiently. And all of this means that you can do operations essentially in constant time, such as substitution. So I guess this is the kind of thing you put at the start of the talk, but this is what a compiler pipeline would look like. And I just kind of want to point out that we're doing something slightly strange, which is we're taking what is a direct style language without without first-class control operators, like a camel. We're CPS transforming it into this continuation passing style IR. We're doing a bunch of optimizing transformations, and then typically we're going to do a kind of inverse CPS transform to get to the target, which might be assembler, say. In the case of the work that I was doing, it was the intermediate language of the .NET runtime. But that's direct style. It doesn't have continuations built in or anything. So you're going to a lot of effort without getting the kind of benefits that are traditionally ascribed to CPS, like being able to do for call CC. But the point is that these optimizing transformations this is a kind of good place to do them, this IR. So I'm going to show you one of those transformations, which is called quantification, that is really quite easy to do when you've got this CPS language, but much harder to do without it. Okay, so here's an example piece of OCaml code. So if you look at this, you can see that the right-hand side of these branches yeah, the point is it's always going to return to the same place. Okay, so it's just the result of the match is then passed to G, and both branches are calling F. And so you can actually turn this into something which doesn't need a lambda, doesn't need a function definition. It just needs a continuation, a basic block, and be compiled much more efficiently. Now, there was work on this by Matthew Flirt and Stephen Weeks a few years ago, where they used some kind of dominator analysis to determine it. But it just kind of shows up straight away when you CPS transform it into the language I described. So let's take this program and CPS transform it. And what you notice is that every use of f, the function, gets past the same continuation, okay, k prime, which means that you can inline that continuation. So it's just like a common argument. But first, we need to kind of hoist it so that it's in scope of the function, because k prime is defined below here. But if we hoist it up here, then it's in scope. And then we can just replace the function with a continuation. And substitute in the continuation for the function call. So instead of a function call now, we've got a continuation call, which is just a jump. Okay. So we've turned what was a more expensive thing to implement, a function call, by something that's very cheap, just a jump. And this generalizes to mutually recursive functions, but it's really just a kind of common argument elimination. And you can basically iterate this reduction, this optimization on a whole program, which gives you what Matthew Flirt and Stephen Weeks called optimal quantification. But it's a completely local transformation, whereas they had to do this dominator analysis. And for real programs, a surprising number of functions can be turned into continuations. Okay, so now I'm going to say just a little bit about imperative languages, having looked at functional ones, because I did mention that CPS can be used for those too. So the most common intermediate form that people use to compile imperative languages like C#, say, is SSA. And the point of SSA is that every variable is defined before it's used and assigned exactly once. So it's a bit like a let. But when you've got join points in your program, there's these 5 functions that tell you, well, I find them very hard to explain, and I think many people do. They're not functions, because they're basically going to, this join point here, it says I1 will get I2 if I came down this path, and it will get I3 if I came down this path. So it needs to know what was the flow. So it's not really a function at all. There's something kind of odd, sort of upside down about them. Now, it is possible to give them semantics. This is the work of Delphine Demange and others. But another thing is that, like with the ANF form for functional languages, when you do function inlining, you have to recompute the SSA form. So it's not closed under function inlining. So a few years back, Andrew Appel observed SSA as functional programming. Well, SSA written slightly differently, where you observe that you can just define functions in the language that I described, continuations, that then get past different arguments depending on the control flow. Okay, so you've kind of inverted things. Instead of a phi node, you've just got the choice of argument at the point that you jump to the continuation. So these are like blocks with parameters, I suppose. And this fits perfectly in the CPS language that I described. Function inlining doesn't destroy formness. there's this invariant of SSA, dominance invariant, and that's just sort of scoping. And you can also express loop structure, just using a recursive version of the continuations. What I don't know is whether anyone has taken this seriously. I mean, SSA still seems to be very popular, but there are with variants of it, like gated SSA. I actually don't know of anyone using this kind of CPS-based language for compiling imperative languages. Okay, so that's the sort of first half of my talk completed. I'm now going to talk about something I've done more recently at Meta, which you could characterize as typing with continuations. So I have to introduce a few things, because this is stuff that hasn't really made it outside of Meta very much. So we have this language called hack. So if you go to the Facebook website, or you access Facebook on your phone, then there will be some hack code running on a server somewhere at Meta. It is the most used language at Meta, even though it's not used outside, just a little bit. It is open source, but it's not had much take up. And it's based on PHP, which is a terrible language. This is why they created hack, to kind of improve on PHP. And it runs on HHVM, which is a JIT compiled runtime based on bytecodes, a bit like the JVM. And programs are checked by hack's kind of whole program type checker, which is actually implemented in OCaml. Some of it's implemented in Rust now. And millions of lines of PHP have been migrated to hack. And there's been a whole bunch of bad features of PHP taken out and good features added. So static typing and async, await, style, concurrency are the major things, I think. And it's continually being developed. But what I'm going to talk about now is how kind of type inference works for local variables. So there's a rich type system in hack that borrows ideas from various other languages. So there's a kind of subtyping based on classes and interfaces and traits. There's a notion of nullable types. There is generics or parametric polymorphism, as you'd find in Java or C#. And there's something that you wouldn't find there is structural subtyping, so function types and record types, which we call shapes. Quite a rich collection of types. And it has local variables, but they're kind of weird compared to, say, what you'd find in OCaml, because there's no scoping. There's no declaration. You don't have to declare the type, so there's nowhere even to hang the type of a local variable. It just kind of springs into existence when you first assign to it. So you can think of it as scoped across a whole function, I guess. Its runtime type typically changes during execution, so there are types available at runtime, and these can be tested dynamically. That's kind of not really relevant to what I'm going to describe. Because they don't have declared types, in fact there's nowhere to put the type, we have to infer them. So the hack type checker infers types for locals. And this is flow sensitive. So, and we'll see this in a minute with some examples. So at join points in the program, we find the upper bound of types. We actually have union types in the language. And types can also be refined by some testing, some dynamic testing. So here's 3 programs that illustrate this flow sensitivity. Okay, so let's have a look at this first one. So it takes in a bool. So we declare types on the parameters. At least the type checker doesn't have to infer those. And then in this conditional block, we assign a string to it, and then we call some other function, and then we assign an int. Okay. But in this branch, we've assigned a string, just assigned a string. So, what's the type of x at this point? Well, hack will infer a union type for it, which is int or string. And this type mixed is the kind of top type. So like in Java, it would be Java lang object. And this union type is a subtype of mixed. So this program is correct. It's type correct. Now let's look at this function, which involves a loop. So it takes in an integer and assigns a Boolean to s, and then enters a loop. But there's possibly a break from the loop, okay? And inside the loop, it assigns a string to s. So what happens here? Well, if we analyze this, we can see that if this break is taken, then this assignment never happens. So this could still be a Boolean. So this is actually type incorrect, and hack will flag an error to say, you're trying to return something which might be a Boolean. Maybe slightly stranger still is this example that involves exceptions. So here we're assigning some new object of class foo to some variable f, and then we enter a try block and call some function. And then if an exception is caught, then we assign some different value to some differently typed value to f. So at this point, when we try and call a method on it, hack has to know, well, this could be a foo or it could be a bar. So it had to analyze the control flow to determine that. Okay. So how do we formalize this idea of flow sensitivity for types? And you won't be surprised that I'm going to use continuations. I think in an earlier lecture of Xavier's, he talked about imperative programs and the fact that at any program point, there may be many continuations. And that's the idea we're using here. So there's usually a next statement, not always, but there usually is. And that's the usual continuation, which we call next. But if you're inside a loop, there might be a break continuation and a continue continuation to return to the top of the loop. In a try block, there's a catch continuation, and we also have try finally. So there's a number of continuations that there may be at any point in the program. So here's a small subset of the hack language. So we've got some types, Boolean to mixed. We've got some expressions, and then some statements. And the statements could be assignments. That's just empty, sequencing, conditional. And we've got break and continue and loops. Okay. And we're assuming there's some kind of subtyping relation between types. So for typing expressions, you do the kind of usual thing, which is you define a context that tells you what the types of the locals are that you're going to type that expression with respect to. So an example would be, x has type int and y has type bool or string. And then you can define a judgment that tells you what type an expression has given some context of local types. Fortunately, you're not allowed to do you're not allowed to assign inside an expression. So apart from being able to throw exceptions, they're mostly pure for local typing. But then for statements, what we do is we define another context, which is all the possible continuations. And the continuations themselves have a bunch of local types. So this is what would be valid if you jumped to that continuation. The continuation's got to be safe, assuming those types for the locals. So here's an example. The next continuation assumes that x has type int, but the break continuation assumes that x has type string and y has type bool. So then when we define typing for statements, it's a safety statement. We're saying that S is safe to run if the locals have types given by gamma and the continuations have types given by delta. And then we can define rules for, say, sequencing. So the empty block, well, that's safe, given a typing for locals and the same typing for the next continuation. So the locals haven't changed. Whereas if you're sequencing, then the next continuation had better be compatible with what's coming, basically. So, I mean, it has the kind of flavor of a program logic, I suppose, in a way. And you can even detect unreachable code using this. So if there's no next continuation, then in the context, then we can do anything after the semicolon. We know that S doesn't continue to the next continuation. So for example, it might have thrown an exception or gone into an infinite loop or something. We can actually get that from the typing. So here's a rule for assignment where this is safe to run if the next continuation has updated the local typing to be the type of E. Conditionals are pretty straightforward because you've basically got to have the same typing for both statements, same continuations. There are weakening rules as well, which I'm not showing you here. So you can always, weaken the assumptions. And rules for loops can also be expressed in this. So how do we implement inference for this system? Well, we take a statement and we infer, given a typing for locals, what the type of the continuations that would make that statement safe should be. So this is essentially the sort of weakest context for continuation types, such that this the safety judgment holds. And yeah, I mean you can compare this to the notions in program logic. So here's an example for conditionals. So if you take the conditional, then you're going to infer, you're going to run the inference on the then branch, and you're going to run it on the else branch. And that will give you back two continuation environments that are, represent what's safe for those statements to run. And the result of the whole thing is then some kind of join of the environments. And this is the point at which we're going to compute, let's say, unions for the types of the locals. And there's similar kind of process for all the features of the language. So in practice, hack type inference actually uses three main techniques. There's this continuation-based approach to deal with locals. And you saw that it's got quite a rich type system. There's generics and there's subtyping. And it basically does some kind of constraint solving for that. And it also does a little bit of bidirectional type checking for lambdas. And it works. I mean, we've got tens of millions of lines of hack code, and people will make a change in their VS Code, the IDE, and expect the type checker to come back quickly. And it does that because we do a sort of incremental checking. It's run in parallel, and now actually it's run distributed. And it's efficient, but it's kind of built on these inference techniques. Okay, so that's pretty much it. I'm going to leave you with some references. So what introduced ANF was this paper, The Essence of Compiling with Continuations. And then the work that I did a few years ago, Compiling with Continuations, continued. I don't want you to get the impression that people are in agreement that this is the right way to do compilation, because there are alternative views. Here's one, compiling without continuations. Basically takes what we did and says, well, maybe not. The exceptional syntax that I mentioned earlier, the SSA is functional programming. That's observing that phi nodes can be represented by local blocks. And this notion of quantification. Okay, thank you very much.